we are going to see how we can convert this pressure into the nodal load. Already we have discussed that the pressure need to be converted into UDL load. The pressure you have 100 MPa. If you multiply with the thickness, then it will be UDL load. That is your UDL load. Okay, now we have the UDL load. In this edge, now from the visualization, you can see the half of the load will be carried by this node and half of the load will be shared by this node. Node number 2 and node number 3 will share the load here. So now what we can do, we can convert this UDL load into the nodal load. 100 MPa there, so 100 into 10 to the power 6 Pascal. Then we have 0.005. Then we have the length, your 0.3. This is the total load. Then half of the load will be carried by this node number 3 and half the load will be carried by this node number 2. So here load will act in the degree of freedom 4 and in the degree of freedom 6. Okay. This also we can achieve by doing the integration. We already know that FEM is very standardized process where we used to get the stiffness matrix K by doing the integration over the volume of B transpose dB. For this plate problem, for this CST element problem, what we can do, the integration for the volume dV we can write as A times the T. A is the area and T is the thickness. So this will give you the volume. So here this part we can write A times T, then in bracket B transpose dB. That will be your K matrix for element 1. Similarly, we also can do for the element 2. Now here you just see we need to calculate the D matrix, we need to calculate the B, we also need to calculate the area. Then we can basically calculate the K matrix for element 1 and the element 2. Now here you can see for the plane stress problem. For the plane stress problem, we can write the D matrix in this format. Okay, so D matrix will be like this. Already we have discussed this part in theoretical portion. Now we need to calculate only the B matrix. Okay, and for the CST element, we can calculate the B matrix using this formula. Here you can see this part where B is equal to 1 by 2A. A is the area of the triangle, area of the CST element, and here this is the B matrix. Now B is basically nothing but this small b's. Small b's are nothing but the difference in the coordinate. Okay, so here you can see y2, y3, y1, all the values are there. Here x1, x2, x3, all the values are there. So this is nothing but the coordinate of the element. Yeah, we can calculate area of this triangle. Area of this triangle will be half times the base and the height. Base is here 300 mm, height is here 100 mm. So basically half times 0.3 times 0.2. Okay. Now what we can do? Now you can calculate the small b1, b2, c1, c2, all the values. Okay. So b1 is nothing but the y2 minus y3, y2 minus y3. So here E1 y2 minus E1 y3. So here what is E1 y2? E1 y2 is nothing but the coordinate, nothing but the coordinate, nothing but the coordinate for the element 1, y value basically for the node number 2. Okay, so this way basically we can calculate the B matrix. Okay, now once we are able to calculate the B matrix, once you are able to calculate the B matrix, we can calculate the K for the element 1. Okay, for the element 1 is nothing but your A times T in bracket B transpose dB here. Instead of B, we are writing B1 for the element 1. Okay, so we can calculate stiffness matrix for the element 1. Similarly, we also can calculate stiffness matrix for the element 2 for the same process. Using the same process, we can calculate the B2. We also can calculate the area of it. Okay, and then we can calculate B transpose D B A times T, that is the stiffness matrix for the element 2. Okay. Now we need to do the assembly of the stiffness matrix. Already we know that global numbering is 1, 2, and the 4. Local numbering is 1, 2, and 3. So here you can see this 1 and this is 2. So degree of freedom 1 and the 2, 3, and the 4 are same for element 1. So what we can do? We directly can fill up to the 4 by 4. Okay. And already discussed in the theoretical part that local numbering 5 and 6 is corresponding to the global numbering 7 and 8. Okay. Those values are corresponding to 5 and 6 must be in the 7 and 8 of the global K matrix. Okay. So this way basically we can fill K1 into the global K matrix. We consider the second element. Our global numbering is 2, 3, and the 4. Local numbering is 1, 2, and the 3. So here you can see, here we have some logic. So here global degree of freedom is 3 and the 4. Local is your 1 and the 2. Global is your 5 and the 6. Local is your 3 and the 4. Global is your 7 and 8. Local is your 5, 1, 2. This is your 3, 4, 5, and 6. Okay. So here you can see there is a gap of 2. 1, 2, 2 to 4, 3 to 5, 4 to 6, like that. Okay. So where what we can do here, we can fill the global K by adding +2 on the row and +2 on the jth values, and we can directly basically add the stiffness matrix corresponding to the element 2 into the global matrix. We can add, we can combine, or we can add the stiffness matrix of the element 2 into the global matrix. Okay, now here we have obtained the global matrix. Now here we are basically applying the boundary conditions. We are eliminating the row and the column which are the restraint. Here you can see we have restraint degree of freedom here 2, restraint degree of freedom. So here you can see this is no degree of freedom 1, degree of freedom 2, degree of freedom 3, and the 4, 5, and the 6. Here we have the 7 and the 8. Okay. Now we have the boundary conditions on degree of freedom 2. Here in this degree of freedom 5 and 6 and the 7 and 8. Okay. So we have to eliminate corresponding row and the column there. Okay. So here we are eliminating this. Here we are eliminating row and the column using these comments. So here we can obtain the global K. Okay, global K after applying the boundary conditions. Okay, let us discuss about the force vector. So here it should be force vector. And please do some correction. This is the correction here. This would be 75,000 Newton. This value is coming from this pressure. 75,000 is coming from this applied pressure here. So here 100 MPa there. So 100 MPa. Then need to convert to the Pascal. Now here Pascal means Newton per meter square. If you multiply with the thickness, then we can convert to your UDR load, and then again if you multiply with the length here, then we can basically have the total load. This is the Newton now. Total load by 2. So this amount of load that is coming here, 75,000, is coming in this node. This node. Okay. So here minus sign indicate it is acting downward, and plus sign is indicating it is acting upward. Okay. So this is the force acting in the node. So here in the node means here we have third and fourth degree. So here the 75,000 load is acting in fourth degree, 6 and the sixth degree. Okay, since there is no horizontal force acting here, so degree freedom 3 and the 5 is free from any loading. Okay. Therefore, now we have force vector of 3 cross 1. We have the stiffness matrix of 3 by 3. We can obtain the displacement from it. Okay. Now once you get the displacement, we also can calculate the strain, and the stress. So you already know the strain that is equal to B times the displacement quantity. So B matrix times or displacement vector. Okay, so for the element 1 and for the element 2, we can calculate. Okay, so for the element 1, we have the displacement vector. Okay, and you already know the V1, we can multiply, we can get the strain. Okay, and if we multiply with the D, we can calculate the stress quantity. Here you can see D times V1 times D. This is the stress acting in the element 1, and this is the stress acting in the element 2. Okay. On that description section of this video, what you can do, you can directly copy it and paste it. If you run it in the MATLAB, you can get the same result. So here you will see how I'm going to run this code in MATLAB. Here, this is the MATLAB code. So first portion is material properties, and here we have calculated the D matrix, and here we are defining the coordinate values. Okay, that is the global coordinate value. Now here for the element 1, we are defining the coordinate and corresponding to the node number. Okay. Now here we are calculating the area of the element 1, and then we are calculating the B1 matrix, and then we are multiplying and will B1 transpose dB1, and then multiplying with the area times the thickness. So here we can calculate the element 1. Here we can calculate. Here we can calculate the stiffness matrix for the element 1. Similarly, we also can do for the element 2. Okay. Element 2, we can calculate the stiffness for the. Here we also similarly we also can calculate the stiffness matrix for the element 2. Now we are going to find the global stiffness matrix. Already we know that size of the global stiffness matrix is 8 by 8 because we have 4 nodes and each node we have 2 degree freedom. So total size of the global stiffness matrix will be 8 by 8. And for each element, size of the stiffness matrix is your 6 by 6. Now here basically we can obtain the global stiffness matrix by adding the stiffness matrix of each element into the global matrix. Here we are adding the stiffness matrix for element 1. Okay, this part basically for the stiffness matrix element 1 into the global stiffness matrix, and this part basically we're adding the stiffness matrix of the element 2 to the global stiffness matrix. So here we have total 8 by 8 size. Okay, now this portion we are applying the boundary conditions. We are elementing the rows and the column by using this comment bracket option, and we have obtained the force vector, that is your nodal vector, that value is your 750000 Newton. Basically here we have converted the pressure load. Here we have converted the pressure into the nodal load. Okay, now here we can solve it. If you run it, we can basically get the displacement quantity. So displacement quantity is coming 0.0017 replace rate 0.0056. This is the solution we got from the our hand calculation. Okay, so this way basically we can obtain the displacement quantity. Once we obtain the displacement quantity, we can basically get the strain quantity as well as the stress quantity. Strain will be B times displacement and stress will be D times the strain. Okay, so similarly, we also can obtain the stress quantity at the element 2. Okay, so this way basically we can solve the plate problem using CST element. What I am going to do, I am going to keep this code into the description portion of this video. You can directly copy it and paste in MATLAB coding, MATLAB, and you can run it. Okay, thank you.